Welcome back, Algebra 2, and this is the last section of Chapter 6 where we're going to look at modeling with the data and writing exponential equations from the data. So first thing we're going to do is a little bit of a review. If you remember first semester, we looked at linear, quadratic, cubic functions. Given the data, we were able to come up with their equations. So when you're looking at data and trying to determine if it's linear, think about how did we know it was linear? We would take the difference of the x values, the difference of the y values, and if you saw a constant first difference, sometimes known as a constant rate of change, then we knew it was linear, and we could then write a linear equation, which you might want to remember this would be the easiest version to use, your point slope version, where m is your slope, and then just take one of the data points and plug in for x1 and y1. If it wasn't linear, then we kept taking the difference of the y values, and if you found that you had a constant second difference, then we knew it was going to be quadratic. That involves solving a 3 by 3, which we won't make you be revisiting this time. Cubic, so it kind of keeps going, any kind of a power function. So linear, constant first, quadratic, constant second. So it makes sense that a cubic would be a constant third difference. So those are ones that we looked at in the first semester. Now we get to the exponential. So an exponential function, let's just take a look at how we know it has the property it has. If I was going to graph y equals 2 to the x, so if I were to plug in 0, notice 2 to the 0 would be 1, so I'd be right here at 1. If I plug in 1, I'm going to get up to 2. If I plug in 2, it's going to go up to 4, so suddenly it kind of jumps. And if I plugged in 3, it would jump even further up here to 8. And that's why we say things grow exponentially. They're not growing at a constant rate. It's getting bigger and bigger and bigger. So as we're going over in the x values, we're going over very incrementally one at a time. But in the y direction, we're multiplying each time to get to the next value. So for that reason, exponential has an add multiply property to it. And because a log is the the inverse of an exponential function, we're not going to be doing these with the data, but I figured it's worth mentioning. It would have a multiply add because inverse functions switch the x and the y and what happens to each. Okay, so we're going to look at some data here and see if we can tell what type of function we have. So this first one, notice I'm going up by 1, so it's all good, up by 1. So we are adding in a constant rate on the first half. This bottom one, as you look along the row of the y values, it looks like we're multiplying by 2 each time. Times 2, times 2, times 2, times 2, times 2. So up here we have an add property. Down here we have the multiply property, and that is indicative of an exponential equation. And just a little piece of information that might be helpful when you're going to write your exponential equations, your base will always be what this constant multiplication is. Okay, so let's take a look at this next one. Let's see what's going on. So I see I'm going up by 2, up by 2. So these all have an add property on top, constant rate there, but in the y values, so this first one I subtract 2, then I add 2, then 6, then 10, then 14, then 18. So obviously it's not linear. It's also not exponential because we're not multiplying. And remember, multiplying, you can multiply by a fraction. So basically multiplying or dividing would be the same thing, but we have neither here. So let's take our second difference. This is going up by 4, up by 4, up by 4. So this is characteristic. The second difference is constant, so that means we have a quadratic. And okay, so you want to be able to, given a set of data, determine what type of equation it is. Now let's say you had to then also write the equation, especially if it's exponential. So for an exponential function, I do this a little bit differently than the book. I take the parent function, which is right here. So we have y equals a times b to the x. And we have two coordinates, two xy coordinates. And we need both. We need two because we have two variables we have to solve for, both a and b. I like to start with the bigger one and fill in for the y and the x. So 54 equals a times b cubed. And then I take the second one and I put it right underneath. So the y value is 6 equals a times b to the 1. And because everything here is multiplication, I divide the two. The reason why I put the bigger one on top is so I don't have to deal with a fraction. So 54 divided by 6 is 9. The a's will cancel, which allows me to solve for my b's. And so now we're dividing the bases, so we subtract the exponents, just like with logs, division and subtraction go together. So this becomes b squared. And so then I'm going to take the square root. Now the nice thing is you don't have to worry about plus or minus. Your base will always be positive. So there's my base, there's b. To find a, I'm going to substitute that into either original equation, but I'm going to choose the one with the smaller exponent on the b. It'll make it easier to solve. So I have 6 equals a times 3 to the 1. And so then we can see that we can divide by 3, and we get a is 2. Once you solve for a and b, you put it all back together into your parent function. Y equals a times 3 to the x. And remember, the 2 and the 3 do not combine. 2 is a coefficient. 3 is the base of an exponential. So please do not combine those as 6 to the x. It's 2 times 3 to the x. All right, and that is your final answer, and that is it. We're done. That was it for the chapter.